Welcome to the second lecture on momentum. During this lesson, we're going to be talking about impulse and how it relates to force. So first, we're going to discuss how force and impulse are related. And secondly, we're going to describe what's called the impulse-momentum theorem. Then we're going to use that theorem to help us solve problems. So let's get started with a little thought experiment. You know that when you're driving a car, they often contain airbags, and you have a seatbelt. Well, why? Let's take a look at what you have at the start. If we're looking at the momentum you have to start, we know that your velocity as you're driving down the highway is very large. If you were to come to a sudden stop, if you were to run into something or slam the brakes, at the end, your velocity is now 0 meters per second because you've come to a stop. Well, your mass stayed the same the whole time. So if I want to look at the change in momentum experienced by you during a crash, I need to take the final momentum and subtract from the initial. Well, let's take a look. No matter how you come to a stop, whether you have an airbag or not, you're going to have the same change in momentum because you have the same change in velocity. So why bother with an airbag if your change in momentum or your impulse is the same in both scenarios, with or without an airbag? Well, there's more to impulse and change in momentum than just the mass and velocity. Impulse can also affect the amount of force you experience. So let's break that down. Impulse is related to force because impulse, remember our J, can be imparted on an object by applying a force to it over time. So we have the equation for impulse so far. The impulse is the change in momentum, which is true. However, we can also relate impulse to a net force over a period of time. We can also show this relationship graphically, where impulse is the area under the curve of a force time graph. So here we see a force time graph. If I were to find the impulse, what I would need to find is the area. So let's shade, here's my area under the curve. And we know that this is a triangle. So I would solve for area 1/2 base times height. Well, let's plug in what we know. If I want to find the area, I've got 1/2. My base is 40 seconds. And my height is 100 newtons. So according to what I get in my calculator when I plug that in, we've got an area under the curve of 2,000, and I'm going to keep my units, so I have newtons and seconds. That area under the curve is the impulse I'd experience. But wait, hopefully you've asked a question about units, because up to this point, we've talked about impulse as a change in momentum. So we've shown that impulse has a units of momentum, kilogram meters per second. But I just described an impulse as a newton second. Are those two things the same thing? Well, let's just break it down. We know that a newton is a force, which is a mass, kilograms, times an acceleration, a meter per second squared. And then we're going to multiply that force by seconds. So let's do a little bit of quick math here. Our seconds and the seconds squared cancel out. And we're left with, guess what? Kilogram meters per second. Good news, our units are the same. So impulse can be represented by a kilogram meter per second or a newton second, as both these units say the exact same thing. So let's do a quick example. We've got a 0.1 kilogram egg that moves at 20 meters per second, and it's brought to rest in 1 second. I want to know the force applied to stop the egg. So I'm going to go over to the side and make a quick note of what we need, what we know. 0.1 kilograms, the velocity, is 20 meters per second. It's brought to rest, so our final velocity is going to be 0 meters per second in a time of 1 second. I want to know the force. So the first thing I can do is say, hey, I know the impulse is the change in momentum. In other words, the momentum final minus the momentum initial. So I can solve this by using the mass times velocity final minus the mass times velocity initial. So I'm going to plug in what I've got. Mass, 0.1 kilograms. The velocity final is 0 meters per second. Mass at the end, so 1 kilogram. And our velocity was 20 meters per second. So if we solve this for the impulse or the change in momentum, our first term cancels, and we're left with a value of 2 Newton seconds. Well, that's cool, but we're not done yet. We're looking for a force. So now I can pull out the equation that J equals Ft. And we want to find force, so I'm going to take J, divide by T, and that'll give us our force. Let's plug in what we know. Our impulse is 2 Newton seconds, and the time from our givens is 1 second. So the force experienced by the egg, applied to stop the egg, is going to be 2 divided by 1, which is 2 newtons. And that's your conclusion. So, now that we've done an example, let's talk about an impulse momentum theorem. Impulse is the change in momentum. We know that already. So I can substitute in delta P for impulse, and that's equal to Ft. And we can break this down even farther because we know the change in momentum is the mass times the velocity final minus the mass times the velocity initial, and that's going to be equal to Ft. And that is your change in momentum theorem, relating the change in momentum to a force times time. Now the negative is important because impulse and momentum are vectors. So the negative simply tells us the direction the object's moving in because direction will matter. So take a look at a quick example. If I'm going at a certain momentum, mass times velocity, in a truck, and I run through a hay bale, I'm going to experience a large amount of time to bring me to a stop, and thus the force I experience will be kind of small. In the same scenario, if I have the same initial momentum, and I stop suddenly in a wall because the time it takes me to stop is so tiny, the force I experience is huge. But in both of these scenarios, the impulse is the same. The change in momentum is the same no matter how I come to a stop, because I've started with the same momentum and I'm ending with a momentum of 0. Change in momentum of 0. Sorry about that. So let's take a look at a quick example. How long would it take to stop 225 kilogram car moving 20 meters per second west if a force of 8,450 newtons to the east was applied? So first thing I want to do is determine what's my positive and what's negative. In this scenario, we're going to call the east direction positive. Remember, the signs just mean the direction. So let's write down what we know. Mass since it's west, we're going to give it a negative. And that's to the east, it's going to be positive. We're looking for how long? We're looking for a time. So let's set up our momentum theorem. We've got mv final minus mv initial equals force times time. I want to get time by itself. That's what we're looking for. So I'm going to take time, divide by both sides, mass by final minus mass velocity initial over time. That's going to equal, over force. That's going to equal our time. And let's solve this. Our mass if you do a little bit of quick math here to get our time, when you plug it in your calculator, hopefully you get a value that is close to 5.33 seconds. And that is your value for time. Now there's 3 more problems on here I encourage you to do on your own, and just take a look at the answers that I get in order to check your work. Be careful about the direction the objects are moving in. So how long would it take to stop 1,500 kilogram car moving 15 meters per second west, as the force of 6,500 newtons to the east was applied. So in this scenario, I'm just going to define east as positive again. So I'm going to make sure I'm consistent. I'm looking for how long it would take to stop. So my final velocity I know is 0 meters per second. The mass of my car is 1,500 kilograms. I've got an initial velocity of 15 meters per second, and that's to the west, so I'm going to make that negative. And a force of 6,500 newtons is applied. That's to the east, that's going to be positive. So I'm going to plug this into my theorem one more time. I've got change in P is equal to momentum, mass times velocity final minus mass velocity initial equals a force times time. Let's get time by itself, since that's our unknown. I've got mass V final minus mass V initial over force equals time. Plug in our values. If you do a little math here, you're going to find that this negative causes our answer to be positive, and we're going to end up with a time of 3.46 seconds. Now check that your time ends up to be positive, because that would be a misconception. We can't have a negative time here. Next example, we've got a 2,250 kilogram car moving at 20 meters per second west, with a force also to the west applied to the car for 1.5 seconds. We want to know the final speed. So first thing I want to do is, since both of our vectors are going to the west, I'm going to make west positive just to make life a little easier. Let's list out our givens. And let's put our theorem here. We're looking for the change in momentum so we can find the final velocity. Mass times V final minus mass times V initial equals Ft. I'm going to get mass times V final. Sorry, I'm just going to write that again so you can see it. V initial equals force time. Let's plug in what we know. We've got the mass, 2,200 kilograms, times a final velocity, which is what we're looking for, minus and that's going to be equal to our force we do a little bit of quick math here. We're going to get that our final velocity minus 20 is going to give us 5.63. We can solve for final velocity by adding 20. We'll get an answer of 25.63 meters per second for our final velocity. One more sample problem. We've got a car, again, it's moving with a force to the east at 15 meters per second west. So for this problem, I'm going to define west as being positive, just because I think it's easier. Either way you do it, just make sure you're consistent. And I, again, want to know the final speed. So I've got V final is equal to since our velocity is to the west, I'm going to make it positive. Since our force is east, I'll make it negative. And let's solve our theorem again. Mass V final minus mass V initial is Ft. Let's get it so we've got mv final. Let's add this to the other side. So we got ft plus mvi. If we divide both sides by m, we'll get v final equals force T plus mvi over our mass. And now we can solve for v final by plugging in our variables. Force, negative 6,500 newtons, time, 2.5 seconds, plus a 1,500 kilogram mass, and our initial velocity of 15 meters per second, all over our mass of 1,500 kilograms. If you do a little bit of math here, put in your calculator, what I've arrived at is a value of 4.17 meters per second for your final velocity. And this makes sense. We are going to the west, so that should be a positive value. That concludes lecture 2. Hope practice problems go well. Thank you.